So these are the first two such sources that we detected at redshifts greater than 5 with the Sears data. You can see this broad component superimposed on the narrow H alpha line here. And one of the things that is surprising about these sources is they're extremely high number densities. And so if we just compile a sample from all the different surveys that have found these faint broadline AGN, you can construct luminosity functions. So this is a plot from Roberto's paper and Jade's. We can see that this is basically where the pre-JWST ground-based QSOs live, and these faint type 1 AGN seem to be about 100 times more common than those bright ground-based QSOs. And as we also heard, when we estimate their host masses, we find out that these black holes scatter above the local M-star and black hole relationship. So this is a plot from Fabio Picucci's study where they tried to fold in selection effects, understanding that we might not be sensitive to sources below the local relationship. But in fact, even when you take into account those systematic effects, you find out that this population scatters above the local relationship at a greater than a 3 sigma level. And so this tends to favor an overmassive, or maybe I should say a massive seed production, or scenario such as the direct collapse formation scenario. Now, the ensemble population of these faint broadline AGN are telling us that that black holes are overmassive at early times. We also find individual sources that are showing this. So this is an example of a broadline AGN at redshift 8.67 that Rebecca Larson detected in the Sears data set. Here, H alpha is shifted outside of the near spectrum, but you can also see a broad component in H beta in this case. In this source, we get a mass of about 10 to the 7 for its black hole mass. And if you look at its redshift, and given that black hole mass, there's two potential scenarios for how this thing might have formed. It could have formed as a massive direct collapse seed with a mass of about 10 to the 5 solar masses at redshift 15, and then you can easily grow this thing just via the its Eddington limit to reach its given mass at around a redshift of 9. However, if you propose that this thing is formed via the collapse of a POP3 star with a mass of about 10 to the about 100 solar masses, now you'd have to push this formation epoch back to around redshift 20, and even then you would need to have sustained episodes of super Eddington growth in order for this thing to reach its given mass at redshift 9 or so. And so the ensemble population that we're finding, these faint broadline AGN, do seem to point toward these overmassive black holes at early times. Now, another interesting result that's come out of this population is that about 20% of them have this really unusual spectral energy distribution and have become known to be as these little red dots. These guys have really unusual colors such that they're extremely red in the rest frame optical and relatively blue in the rest frame UV. There's a number of different ways you could produce this SED shape. This could just be a massive galaxy with the AGN light coming out in the blue end. This could be a heavily obscured quasar with host galaxy light contributing to the UV side. Or if you think this is just all unresolved light, this could just be scattered light. This could just be an obscured quasar with 1 or 2% scattered light contributing to the UV side. Or you could end up having just an alternative dust attenuation law. So Martin Gaskell, for example, in 2004, noticed that some local QSOs have an attenuation law such that that flattens off at short wavelengths. So this is lambda to the -1 here. And so this means that blue light will be attenuated less than you might expect given just an SMC dust attenuation law. And that might give you this so-called V-shaped SED. So there's a number of different ways that you could produce this SED shape, and this is one of the reasons why it's been so difficult to interpret what's going on with the little red dot. But regardless of what's actually producing the SED, their unique colors means that you can identify them photometrically. And so several studies have now done this where they've, for example, this is a plot from Guillermo Barro's paper where they're looking at 277 minus 444. Red things percolate to the top of this color diagram, and this is 150 minus 200, and so blue things will move over to the left. And so just using that color diagram, you could start identifying things with this kind of steep spectral slope and this UV excess. So what I wanted to highlight in this talk is some work we did earlier this summer where we tried to move beyond just the color diagrams of selected things and instead try to measure the continuum slope of these little red dots. And hopefully that would allow us to find these things over a greater redshift range than a single color selection. And so what we've done here is we've extended our search for little red dots down to redshift 2 and then all the way out as to redshifts 8 and above. And but what we've done is now shifted we're using different band passes to sample redward and blueward of the Balmer break. And so as the redshift of our photometric redshift of our source moves, we use different band passes to sample the same rest frame wavelength. And so that allows us to measure the spectral slope on both sides of this break. And so we did this in Sears, Primer, Jades, NG Deep, and then Uncover for comparison. And so this is here's 3 examples of sources that we identified using this method. This is a source at redshift 4, redshift 6, and then at redshift 8. And you can see all of these guys feature that really steep optical slope and then this relatively flat blue component here. So using this, we identified about 341 candidate faint red AGN, or these little red dots. We did a lot of work to remove contaminants such as brown dwarfs, which tend to be bluer in the UV than our AGN candidates, and then also some extreme emission line galaxies where we think that the bands of some of these sources might be boosted due to line emission. So one of the main results that came out of this study is a redshift distribution for the little red dots, and so that's what's shown here. Even though we are sensitive to sources that have this spectral, this SED shape at redshifts 2 and 3, we really don't find many of them there. In fact, it really does look like this population emerges at redshift 4, and it peaks around redshifts 5, 6, and 7. And then it peters out. The tail end here may very well be because we simply can't detect the UV portion of the SEDs of these sources. The UV portion is extremely faint, so you can imagine as these things redshift away that we might be missing that UV component, and we required both that red side and that blue side. But on the low redshift end, we definitely could detect something at redshift 3 that had that same SED shape, and we simply don't see them there. And so we propose in the paper this might simply be a natural consequence of inside-out growth, that at these early times we've got centrally concentrated star formation that is in a deep potential well. A lot of that emission can't escape. It basically feeds the accretion out of the black hole with a high duty cycle. And then as time goes on, as star formation moves out to larger scales, they may actually clear out the obscuration of the central source and may actually lead to a drop in the duty cycle. And that's why we're not seeing these things at lower redshifts. Now, with our sample of about 400 sources, we can construct a UV luminosity function, and so that's what's shown here at redshift 5 and redshift 7. And our red points here are our data. The blue points are Vasily-Korkorev's, and the green points are Jenny Green's estimates. They all agree pretty well. Just to give you a sense of how troubling these number densities are, this plot here is this line here is the QSO number density. So these are the QSOs identified from the ground in the pre-JWST era. So the little red dots are a factor of 100 above these things in some cases. But here's the X-ray, the number density of X-ray AGN at redshift 5. All the known X-ray AGN at redshift 5, and we're already above that number density. And this is just for the obscured little red dots. The type 1 AGN that are unobscured are even more common. So that's those points up there. And so you can see in this case, this is the UV AGN luminosity for number density at redshift 7, and we're again above that. We did identify a couple of X-ray detected little red dots. So these are sources that fit our slope, continuum slope cuts, but they are X-ray detected. And so there's a lot of questions about what's going on with the SED of these sources. We find that for this source, this is a source in Cosmos at a redshift of 4.66. We find that the continuum, the optical continuum is well fit with that of an accretion disk, even all the way out to 24 microns. And then this tells us that the blue side should be coming from the host of this source. And in fact, when we subtract off the point source here, we do see telltale signs of an extended host in the source in our bluest band. So this is 115 there. And there's enough X-ray photons in this source that we can actually detect, we can actually perform a model fit of this spectrum, and we find out that this thing has a neutral hydrogen column density of 10 to the 23.3. So it's moderately obscured, not quite compton thick, but moderately obscured. So in agreement with our general picture of what might be going on with these sources. So just as we were wrapping up this study, the data from the Ruby survey became public, and so we had a look at what fraction of our sources actually have broad emission lines. And we find that actually up to about 82% of them, depending on what signal noise you want to cut at, do show signs of a broad component in their H alpha. And so that's what's shown here. The widths here are about 1400 to 4,200 kilometers per second. So a very large fraction of our sources do show broad lines. And again, remember, they're just selected based on their colors and their compact size. And as Hannah mentioned, 25% of the little red dots in our sample actually show blue-shifted helium-1 or Balmer absorption features. The Balmer absorption features are particularly interesting because they tell us that there's dense, low ionization gas present within the dust sublimation radius of these sources. This stuff is moving out at a few hundred kilometers per second, so this is not some kind of crazy outflow that the AGN is powering. It's not clearing this material out on short timescales, but it does tell us that there's a large covering factor of this dense gas present near the central engine. And so I'll just end maybe really quickly with talking about, so there's a lot of open questions about the little red dots. One of them is in regards to their X-ray weakness, as Hannah just mentioned. There's a recent paper by Irini Lambrides that shows that these things actually are 5 sigma outliers in terms of their alpha OX. That's the ratio between their optical luminosities and their X-ray luminosities. And so as Hannah mentioned, Roberto proposed that perhaps this could just be due to a low metallicity gas that basically completely envelops the black hole there. But I will point out that, so that model actually does agree pretty well with the idea that there's these absorption features that we see in these sources. But I will point out that even the unobscured type 1 AGN that we see are X-ray weak. So it doesn't necessarily have to involve obscuring the central engine. Even the sources that look completely unobscured are also X-ray weak. So another potential possibility, as Fabio told us earlier, is just superannuation accretion, which notoriously produces a weak X-ray corona that might not be detected. So I think I'm out of time, so maybe I'll skip this slide and just go straight to my summary and take any questions you guys might have.
Thanks, Dale. Okay, why don't we start? 1, 2, 3, 4.
So thank you, Dave. Yeah. So I don't know if I got this correctly, but...
Sure. Name again, please.
Oh, sorry, Rafael Laschneid. So if I got this correctly, so that the those little red dots which show X-ray emission have a sign of a host galaxy contributing to the SED. Right. So can it be that kind of paradoxically, the X-ray emission is due to star formation in these systems rather than from the central AGN? So have you tried to see if this would fit with the estimated star formation rate?
The luminosities of these are quite high. They would be, I think they're well above 10 to the 42 rays per second, so I suspect that they wouldn't be coming from star formation in the 2 that we detected. They're just so high and they're so bright that the X-ray luminosities are, this is like a log X of 44.7, so it's pretty much, I think, rules out star formation.
Really nice talk, Dale. Priya Natarajan. I was curious, the overlay that you showed of the X-ray AGN at redshift 5, that does not include the expected, very highly obscured Compton-thick population needed to explain the excess hard X-ray background till redshift 5, right?
Yeah.
So I just want to know
right.
by eye, if you fill that in, where do we get?
That's a good question. I don't know where those Compton-thick sources would sit here. This, of course, is type 1 high-Z quasar, so they're like by definition unobscured sources. That's right. Yeah, that's a really good point. I don't know whether you could just fill this in with a continuous.
I was just curious
shading.
whether that would just fill in there.
I don't know that. I don't know that answer. Yeah, that's a really good point, though.
Hi, Dale. This is Erica Nelson. Thank you for your great talk. Okay, I wanted you to talk to me about why we're not seeing them at low redshift. Because your argument was that it's like an inside-out growth thing, and then your argument was that, like, at lower redshift, massive galaxies don't have dust in the centers. But and that's why you're not seeing that same SED. But we know these massive galaxies are really dusty in the centers. Like, I'm thinking about, like, Ken Tadaki's work or something like that. So I wasn't quite sure about the logic there.
Yeah, this was just like a quick back of the envelope. Why do you explanations of why these things might drop off? I guess I was more thinking of as the star formation moved out to larger scales, you've just got less gas feeding that black hole, so the accretion rate drops. Whether there's enough dust there to continue obscuring it, well. it depends on what you think is actually causing the obscuration of these things. If it's the cloud of material around the black hole, then it's completely disconnected with the dust in the forming massive galaxy around it. If you think it's the ISM of the host on really small scales, like maybe 100 parsec scales, then there might be a connection there. But if it's on nuclear scales and there's something else going on, it might actually finally clear away the material after sustained episodes of growth. It's not really clear, but it could very well be that the amount of time that the black hole is on actually starts to decrease as basically the star formation progresses to larger scales. You've got less action going on in the center of the galaxy.
One last question from Joe Kohei, please.
Thanks, Dale. So I guess the most striking thing about both the little red dots and the other JWST AGN that aren't so red is their number density. And so the problem would go away in principle if they were just a lot fainter than people are claiming, right? And you're sort of working in a regime where the galaxy could be contributing some light, and you don't actually measure the bolometric luminosity, you measure broad lines. And then you use AGN scaling relations for type 1s to get the bolometric luminosity, but then the spectra actually look nothing like type 1s.
Yeah.
So can you convince me that you just don't have the bolometric luminosities off by a factor of 10?
Yeah, so this is a really good point, and it's the reason why I didn't include a bolometric luminosity function in my paper, because how you convert to bolometric luminosity is really dependent. You could do it based on the continuum, but you have to assume the AGN is dominating the continuum. You could do it by the HF luminosity, but you have to convince yourself that they're basically like type 1 AGN. So yeah, the number densities that I was showing were basically just straight up observed UV luminosities. And so there, to get around exactly this issue.
But that could be galaxy light, right?
It could be galaxy light, that's right. So if you think it's galaxy light, then they're brighter than you might think they would be. That's right. Yeah.
Thanks.
Yeah.